Thank you so much for having me, and thank the organizers for this amazing program. Tell all my friends it's like a Disneyland for mathematicians here in Cambridge. The Newton's tree. I mean, yeah, it's really great working atmosphere. Thanks a lot. So the motivation for what I'm going to talk about comes from so I wrote in the abstract a slightly different motivation. Then I realized that okay, we're at a conference that really cares about GIT quotients and moduli spaces. So maybe I can actually give the original motivation for this thing. So it's the following. So you consider so you can consider K to be maybe C or Q for Q sufficiently large, and then consider S over K a del pezzo. No, so we could do that, but we can also, it's even more convenient is to consider a smooth projective curve. And then D some divisor with the degree of E strictly big than 2G minus 2. And then we want to look at Higgs bundles with poles, well, meromorphic Higgs bundles. This divisor, so we fix also a number n, 1, and some degree D in Z. And then we consider the following moduli problem. And for D, this will be pairs E comma phi, where E over C is a rank and vector bundle. Of degree D and phi some twisted endomorphism like this, and plus we want them to be there's some notion of semi-stability involved here, and so this would be the moduli space. So this would be Higgs bundles, and we have imposed semi-stability, and so we can go also to the coarse moduli space. And this would try to make it a bit bigger. For moduli space. So it's not actually going to be a talk about Higgs bundles or anything, but just we have one moduli space that people care about. And then the theorem that we proved a while ago with Francesca, Julio, Becky, and myself, says that you can so you can study the intersection. So this space, when R and D are not coprime, in general will be a singular space, and you can study the intersection homology. And there is various reasons to do that. And the theorem, so we noticed the following thing. So it's a finite field version of intersection homologies. So sort of in this function sheaf dictionary, you can look at so in the global sense, you can look at the trace of Frobenius on the intersection homology of this space. So this will be, so the finite field is some vector space yeah, over the algebraic closure of that finite field, and the Galois group is generated by Frobenius. So you can act on this, take the trace of, you have to take alternating traces, and this gives you some number. Okay, and if you know this number for sufficiently many finite fields, you can sort of recover pieces of the, yeah. as a Galois module, you can recover this intersection homology as a vector or as a Galois representation. So this is kind of an interesting quantity. It's close to knowing the intersection homology. And so we noticed that this can be computed, this number, as some integral over the coarse moduli space of some function with some measure. But so this space here we will see later in the talk. This will be some p-adic manifold, or more geometric, you can think of as the arc space of your singular space. And okay, this is some, I will not say much about this function. This is just some sign, basically this will be some roots of unity. And then there's some, which you call orbifold measure, but there's some specific measure on this manifold, and you can recover this sort of cohomological gadget from some sort of analytic integration over manifold. And when I say manifold, you can really, one approximation is the arc space, and the other one is the reals. So it's a bit like a real manifold, and we do just honest real integration thing. So it's a bit exotic, but actually theoretically not very difficult operation. And so the problem, or maybe the question is, is why? So the motivation for this talk was to understand our own theorem in some sense. That's a bit weird, but so the question is, the proof is rather indirect and uses the p-independence of both sides, which for the left-hand side is due to Maulik and Chen-Ruan, who is here. That was maybe I should say the original motivation was the paper of Davesh and Chen-Ruan on this problem, and then we kind of knew that these sort of integrals also have this property, and then you can maneuver yourself into the case where R and D are co-prime, and then it's easy to show. No, it's not. No, it's more. I don't know. It's more related to the shift somehow of the fact that there is some sign in the intersection cohomology. So it's just a sign. But we also have Michael Thaddeus here. Yeah. So it's also related. So it's your germ that you put with Tamar on the moduli of Higgs bundles in the mirror sim. So it's related to that kind of germ picture there. Okay. So the proof is indirect, and so the motivation was to give a direct proof at the left-hand side for the right-hand side, without playing with the D. Give a direct proof. And this doesn't sound like an amazing motivation to reprove your own theorem. But so it's kind of interesting because what you have to do on the way. No. So if they're co-prime, then it's very easy. Then then the space is smooth. This is homology, and then the basic theory will tell you. And I should say, in the non-comprime case, this was singular, and there was basically you could always define this manifold and the integral, but there was no theory before that would tell you anything about this quantity. So when you integrate on a singular space, very little is known about these integrals. And that was maybe, from my point of view, the motivation that even in this very singular case, these integrals, they carry some important information. And so how to get this information out of singular space. And the proof, okay, maybe today, I would like to give a direct proof with this, which will have several features, but basically there's three things one have to do for this proof. So first of all, one has to go from this singular space to something smooth, and the smoothness in this picture comes from the stack. So this guy here, this one is actually smooth. And this is because we have this condition here. That ensure you that the higher X groups vanish. And so there is smoothness somewhere, but just not on the space we're integrating. So we need to understand, basically lifting arcs along this map, pi, which goes from the moduli stack to the moduli space. We have the arc space downstairs, you want to understand the arc space upstairs. And then we need to, and then once we have lifted it, we need to compute. So we have lifted it, we get some integral on the stack, we need to compute this integral. This comes down to some volume formula. And there's sort of, in this integration theory, there's a bit of history on this formula. So this will be some sort of generalization of something that was known for finite quotients by finite groups. And then finally, this will kind of explain the right-hand side. And then we also need to explain the left-hand side, to put it in a similar shape as this volume formula. And this will be the last thing. And this is about sort of BPS invariants, because this is, and formulate this purely topologically in terms of intersection cohomology, but actually very special space. And so the intersection cohomology also plays a very special role from the point of view of the enumerative geometry. Okay. And now, somehow, the point why I think this is kind of interesting is that these two first things, they work for very general, so this works sort of for general, quite general quotients. So here we have the GIT quotient, but basically whenever you have some sort of quotient of a smooth stack, with some maybe singular space, this first part works. So no relation to any moduli space, no general quotients. And this one also works quite general. For sort of smooth linear moduli. And the sort of, these are kind of, so this integration theory motivated this sort of new, maybe I should say, so new formula. For BPS invariants, and this kind of new formula came out of the integration theory, but you don't really need to say anything about integration. You just care about these formulas, but those. Yes, exactly. In the end, that is kind of the nice applications. We get a very different sort of p-adic analytic proof of the independence of this IC on the modularity. And
the last part basically depends on quantifies our models that depend on the local structure.
Yeah, no, but in this case, it's really, it's a smooth, there's no potential or anything. It's really just vector space by a group. So, but yeah, it does depend on that. Yeah, it depends on hom on X. Yes. But it's just, so we have a stack over K, such that for every extension of K, the K points of your stack form an abelian. That's our approach. So vector bundle. So this could be vector bundle on the curve, or representations of quivers, or sheaves on a Del Pezzo surface, one-dimensional. Yeah, so this category, it will already be one of these. So it will be semi-stable things of a fixed slope or something. And then you won't know higher x. X2 values. X2 and higher. Yeah, for regular Higgs bundle. No, in fact, that's exactly the tricky part. If I have time, I can say. Why we have D bigger than. Okay, but okay, the more I talk about this, the more I like the first part the most. So that's high lifting. Because it's really a very general thing. I imagine I've not seen this anywhere else, but some people must have written this in a different language. But I think it's a very cute picture. So now I need some notation first. So F will have to be over QP finite extension. And in here we have O, the ring of integers. We have also K, little k, some finite field. And in this ring of integers, so this is a principal ideal domain. So some uniform so generator of the maximal ideal. And then if you're not at all familiar with QP, you don't lose anything. You can think of F, of this field F, as sort of being the same as the power Laurent polynomials in this uniform. And O, this would be power series. In this uniform. Never mind, it's this. Now, everything I say is, many things will be wrong in this case with the finite field, because it's not a perfect field. But for the first approximation, it's fine to think like that. And then we also need ramifications of this. So you know, by Fn, the field you obtain from F by adjoining some nth root of the uniformizer. And then in there, I have On. And more importantly, I have this D 1 over n, which is just a spectrum of O of n. And then I mod out by mu n. So this is sometimes called a root stack along or the root stack along the divisor given by the maximum. Okay, so that's the notation for the base. So we will think of O points. O points look like power series points, so they look like arcs in your space. Some arithmetic version of the arc space. And then so that's why we have this D for disk. So D1 over n points, we think of them as sort of twisted arcs of your space. And so I was very vague about the quotient. So what's the actual situation we want to study here? So we'll have U over O some variety, and G, so linear algebraic, over O, and we want an action, so G. So we can only do sort of global quotient stacks. So G acts on U. G acts on U, and we have a morphism, which we call phi tilde from U to some X. So I should take two spaces, X and U. So I want to say that X is the quotient of U by G, but in fact, I just say that this should be G invariant. Or in other words, we have a map pi from our sort of stack, which is, sorry, it's small. Yeah, pi would be the map from the stack to X. And there's one condition, maybe the most important one, is that so the important condition is that such that there exists a V inside U smooth and open such that if I restrict my map pi to the V, this one is an isomorph. So it's a way of saying that generically the action should have no stabilizer. But more than that, also generically the action should somehow not contract. So these orbits where G acts free should not be contracted, or at least an open set of those should not be contracted. So in other words, this should be generically a G bundle, G principal bundle. Oh, yeah. Yeah. Where's the oh, there it is. So yeah, we just took some. So in most cases, yeah, this will just be some sort of GIT situation where we have an open dense locus of stable object, and that works. But okay, you always try to make things as general as you can. Okay. So let's basically we have this map pi, and we want to understand. So how does pi inverse of X look like for some X, which is an arc in X, and maybe we want generically we want the generic point of this arc to be in this locus where the stack and the space are the same. So instead of yeah, trying to explain this further, let's just what I mean. It should become quite clear. So let's look at GM acting on a 2 with weights 1, and we can take the pi tilde. So we can take the GIT quotient is basically A1. And the map sense XY. Quotient. And so in this case, let's give ourselves an X and X in here. So that is an X in A1. So V would be A1 minus the origin in here. And then take so an element in here. That's just an element in O, which is not in here. So we just remove it. It can be any power series, but not the zero power series. And then, so what's pi inverse of X? So maybe the O points of that. So basically, you need to you need to give me two power series such that their product is X, or maybe let me call it Z. Yeah, you need two power series X and Y such that their product is Z. But everything has to happen in O, right? So that means somehow the T valuation or the omega valuation, the var pi math. So the valuation of X and Y cannot be bigger than the one of Z because then, yeah, you only have positive valuations. So basically what happens is here, so get so for example, one image will be to point 1, comma Z. Right? And you can always act by GM of O, and this is GM equivariant. You get this, but GM of O will not change the valuation. So you can have 1 on NZ, and then you can also have omega and then Z over omega. And again, you can act with GM. So let me just act with GM everywhere. And you can go on, and you can go on up to the point where this does not lie. Well, where this does not lie anymore in O, when it has some omega in the denominator. So the highest one, basically omega to the valuation, Z divided by Z. And so we see two things. So the pre-image is somehow finite union of this G O orbits, and there'll be finitely many, and the number kind of depends on the valuation. So the number of those varies. But if we just care about the number, then we can just look at the valuation, for example, in one of the coordinates, and that will be here. Valuation will be 0, valuation will be 1, and here will be valuation Z. And so we get some sort of subset of the integers. Yeah? And so the weak form of the first theorem is that this always happens. So where does these integers come from? Well, it's really the valuation. So you should think of these integers as being this quotient. So this GM of O, this is just no, this is the units. Oh, it is all the power series start with a constant term. So this will not change the valuation, but basically, once you mod out, what the only information is left is the valuation of your Laurent polynomial, or sorry, your Laurent series, and that's some integer. And these are exactly the integers. And so now you see if you do this for a general group G, then you expect something like G of F mod G of O, and that sits inside the building of G, if G is reductive. And that is indeed somehow on the level of O points, that's the theorem. So we need some more conditions that if back X is called S complete. So that even so S is the same S as for S equivalence. But yeah, so basically, if you think in terms of GIT quotient, they will always be satisfied. We also assume maybe that pi inverse XO is not empty. And then this fiber should also be reductive. I should say here people care about non-reductive things. Somehow in this setup where we care about the stack, we can always change the presentation of the stack into something. So G can always be GLN. This is somehow not the issue here. Yes. 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 Yeah. Exactly. But yeah, it means you don't want any holes. I can explain maybe later in the example what it means. But yeah. Okay, and then this space so can be embedded as the integral points of a bounded convex region in the building of G. So the building of G is some locally Euclidean W complex. So it's really real topological space, has some integral structure, and GF mod GO are exactly the integral points in that space. And okay, and as this is sort of not a very interesting theorem. We will improve it when we add the ramification points. But the second part is that this pi map so it goes essentially from X, all points of X, I can maybe intersect, yeah. I should intersect. I want again this genericity condition. 2 points of little x, F. So this is about the finiteness. So this is finite eta. So now these are, well, always there's some topology and there's also an analytic structure. So these are manifolds, and then you can talk about this being a covering. And you see it's a covering because you have this GM of O around each point. So this will be a little neighborhood of your point, and over this neighborhood, it's really a covering space. Yeah, yeah, global quotient, U mod G. Yeah, that's a good question, how to generalize. For this, so the problem is for this, you need to have a good moduli space. No. Yeah. I think the problem is with the problem is in positive characteristic, almost no group is reductive in their sense. Yeah. Yeah. But modulo that. But this guy. Okay, so this is so yeah, so this convex region here, this would be this interval. No, I don't think it's really étale with respect to the. It's not étale as an algebraic map. It's étale in the analytic. It's not it's quite a weak. I mean, it's much weaker notion because these spaces are totally disconnected. It's not so hard to cover. So what did I want? Okay, so now I want to also put in the ramification. Maybe I use a color for this. It might be. So basically the picture for now was this. We had upstairs, we have this A2. There's the fixed point, and there's maybe some special orbits. And so here's the origin, and we picked some arc here close by, and then upstairs we get some sort of lift, looks like this, but the valuation cannot go over far, so somehow, yeah, we get some sort of region, and the valuation is. And now we can also ramify, so we can basically ask the same question here. So I can ask what is pi inverse. So I take the same x, but now let me just put d1/2. So then basically, so now I have taken a root of omega. That's the only thing, and I ask the same. Yeah, I want to solve the same, understand the pre-images, but now I have the root of omega. So then this kind of stays the same. And then I still have one of z's, the first one. But then, okay, the only thing happens is that now I get the in-between ones. And the same endpoint. So I get 0, and I also get 1/2, I get 1, I get 3/2. I just, yeah, and also get all of these. So if I ramify, I get sort of more points, but in the same kind of interval. But now I allow my points to not be integers, but having 2s. If I do it for R, I get it for every. And so then with the same conditions, I put here G 1 over R, I get it as the rational points, or I should say 1 over R is the points of the bounded region in a convex building. And here again, this will again be R, D 1 over R. Yeah, I know. So yeah, it's a bit confusing. This twisted points to a stack. So there's some confusion. One has to get around in his head what it actually means. But yeah, maybe the first one I can trust me really means you just have a rule and you solve the same problem here. And so yeah, so you see more. So before being convex was maybe not so convex and bounded for a discrete set of points is not a very strong condition. But now this is an actual theorem. So we get a bounded region every time. And we don't know much of it. It's kind of would be interesting to study this in examples, what it kind of means. So, but you can push this further. For example, you see you always have these. So in this picture, you always have these points here, the extremal points which close up, and they will correspond in your picture to the orbits of maximal dimension, which have your close point, well, which have the origin in its closure. So these 2 points correspond to these. And then you have a whole open part of your region, which will correspond to everything that specializes to the. So here, when you put omega to 0, you go to 0, but here you go to the other orbits, and here you go to the opposite one. So there's a lot, you can sort of, between the arcs and the actual geometry of the orbits, you can kind of play around with this thing. And you also can see, for example, what S-completeness means. So that's the last thing I want to say. So a way to get something non-S complete would be to remove the origin just from, so look at A2 minus 0, and you still have the action and everything. And then what you see what happens is you remove the whole, so you remove a close point here, it corresponds to remove something open here. So you remove everything from this interval but the endpoints. And then you see you get 2 points and it's not convex. It's 2 points. Not connected. So there's some sort of interplay. Yes? Yes. Yes, so there's one convex region. Ah, yeah, it's not good written. Yeah. Yeah, it's one convex region, and you just, yeah, when you look at the R, you look at the different points. Probably very slow. Okay. So this is basically this so structural result about arcs and stacks. And in some sense, it gives you, as we'll see, a way to go. So in terms of integration, it kind of makes your dream come true. So you can go from the quotient space to the quotient stack and back and forth in a very fluent way. So this chapter about integration, right? So we let mu be a R measure on F. It's our local field such that mu of the ring of integers just O. Yeah.
So the first part, where is the place that it's smoothness?
There's no smoothness. Yeah, there's no smoothness here. No needed. Yeah. Just this V, they want some generic locus which is smooth. That's all. That we always have. No, this can be just generically, it has to be the coarse model. Yeah, that's right. So we have a Haar measure here. And then, so there's this whole theory of analytic manifolds, which I don't want to explain, but so if you have F some manifold over F, which now you can think of F as being the reals, and then it's really the definition of a real manifold. So you have such a manifold, and you have omega is some top dimensional form, then the integral of M over the absolute value of that omega is well. So that's somehow something like in the reals. And here the absolute value just comes from the fact that the Haar measure on this field F still takes values in the reals. And this is the one in the real numbers. So you have to integrate real or complex valued functions. That's why we take the absolute value of the form omega. So that's the asymmetry one has to accept. And so in particular, this is where the integration comes from. Whenever you have some variety x over O, any variety, and you have some form omega, which is an algebraic top form on the smooth locus, on the smooth locus of x. In fact, even the smooth locus of the generic fiber of x, then then I can look at the integral, the absolute value of that on that form on the O points. But only those which are generically smooth. So because this part, if you have a smooth variety, then it's kind of clear that the points of that variety form a manifold, some sort of inverse function theorem. And so I can integrate that, but this tends to not be a finite number because this is, well, it's not compact. But if you impose the O, if you only look at the O points, then that tends to be a compact, well, it's not maybe a compact space, but it will have finite measure if the form is reasonable. And so that's sort of the integration theory. But in our situation, so if we have pi, so now for integration, maybe we want smoothness, but okay, we don't. Now it's as above. Then and we take some omega a top form on U. Sorry, on V. Then right, V was this set which V itself was smooth, and it kind of sits in both spaces. Then I can try to compare the following integrals. So right, I can look either at the elements in V of F that are also elements of the arc space, and I can do the same. X omega. And I can try to compare the two. Now in the example, basically it corresponds to either looking here, right? Either looking on this line or at the lifts. So this was no, sorry, either looking at just the point X or all the ML elements in the pre-image. So this will all be this. So typically, because this stack is not separated, you have much more points here than here. But the theorem before, because this is basic, so we see we have a map, we have this pi map here, and this is finite et al. So typically, it will tell you that you get the same thing if you count the number of things correctly. So here you would have to count the number of elements in the fiber every time. So if I count every point x with the number of fibers it has, because it's a covering, then it's very easy. So that is not very difficult. The problem is you want to get, so I mean, this is exactly applying such a formula is exactly kind of knowing, pretending to know what this coarse moduli space map does. It's a difficult thing to understand. And the idea is to get rid of these numbers by using the ramifications. So inverse of x using the ramification, and then this what I would call polytope combinatorics. So this is Stanley. So it's basically when you have a okay, Stanley proved it when you have a rational polytope inside Rn, then you have this formula that if you take the sum and you count the rational points for each denominator, call it R, and so for us this will be pi R inverse of x. So yeah, okay, this lives in the building, so it's not quite a polytope, but pretend it is a polytope. And you look at this series of all the rational points with a given denominator, that's a rational series. And if you take minus the limit, so it's a rational series, if you look at the limit, then here you should get the 1. That's the thing you want to get. And so, so yeah, so it's bounded Euler characteristic of the polytope. And so the theorem, so basically we use this to get rid of the this again. We use this to not having to count along the fibers of the map pi, of this quotient map, and we can then relate the integrals on the two spaces follows. Second theorem. So again, there are some assumptions. So assume there exists G invariant, Zariski locally, I should say. Locally G invariant trivialization of omega u. Oh, I should also say we assume that u is smooth now. So this is the first time we need smoothness, yes, for the stack. And then we want this to be so it's another way of saying that you want the canonical bundle of the stack to be Zariski locally trivial. But you can formulate it this way. And then we again have that x should be, so x smooth, remember x, the quotient of u by g would be x complete. And then there is the final condition, which says that every point, so you want to integrate on this space here. And okay, if you we want to at least say that we can see all these spaces from the arcs on top. So we want that the union over all these x be 1 over r again. Vf. We want this to be surject. So that every point lifts to some finite ramified disk upstairs. So this is somehow so in the case of a moduli problem, this follows usually from Langton's type, a Langton type theorem. You have to want to extend some family of over the generic point of a DVR to the full space, but it's a condition. And if you have these conditions, then there is a canonical measure we call this orbifold measure, such that if I want to integrate over my space, yeah, and I get this funny looking formula. Which looks a bit like this statement from Stanley. But now I've hidden one step. So this step allows me to go from the space to the stack. And now the stack is smooth. And there's a second space step, which I will not explain. But if you integrate on something smooth, then you can actually get an explicit formula. And the formula is this, that you have to count something, and you have to count homomorphisms from the classifying stack of mu r into your original stack. And you do this for every r, and you build some series, and then you take the limit. Where I have to explain to you what the W is. So W is a map from these homomorphisms into integers. So what does it do? So here, this is not such a scary object. So an element in here, so I should say over the rest, sorry, you count over the finite field K. So an element in here, it's basically, it's a point X. So an element in here is a pair X on phi, where X is a point in your stack and phi is a map from mu r into the automorphism of your point pair. And then to that, you can associate a function. It's basically send this to the weight, sum of weights of the mu r action on the tangent space. So mu r acts on this, it's an automorphism, so it acts on the tangent space, on the tangent complex in this setting, and then yeah, and then you add up the weights with the multiplicity. And there's one in degree 0 and one degree -1. There will be signs involved, but some local. Okay, so that's the formula. So maybe, so one nice thing is, right, 2 remarks. The first one is that this covers the orbifold formula or orbifold cohomology when G is finite. Or when, yeah, or when maybe you could say when X is a Deligne-Mumford stack, then in fact there is, yeah, you can see there's probably only finitely many such morphisms from mu r. So the sum is just a finite sum. And you exactly get, yeah, we get the trace of Frobenius on orbifold cohomology. This was the case that was known before. but it's some sort of generalization for any group. And the second one, and I think this is a very nice audience in this workshop, is there's no cohomological interpretation in for the right-hand side in general. Right? So if G is finite, then it's this orbifold cohomology, but in general, some quantity, if you just ignore all this, some quantity you can write down for any stack, some reasonable property, yeah, some property like this, and then gives you some number, and a number should be the trace of Frobenius on something. So yeah, it looks like there should be some sort of orbifold cohomology for arctic stacks. That would be really nice to figure out, but it's really hard to deal with this operation that involves the limit. Okay. So I started a bit late, so I have like 3 more minutes. 5 more minutes. Okay. So then let me quickly go back to the motivation. Where M was our stack of Higgs bundles. So that fits into the picture. And basically, the combination. So how do we get back to this intersection cohomology? Is now is that we don't directly relate to intersection cohomology, but basically, yeah, the intersection cohomology, the trace of Frobenius on intersection cohomology should be given by some sort of formula like this. It's very, very curious. And the way to do this is that we just verify that both sides verify the same sort of recursion. And the first recursion is due to a theorem of Meinhardt. And it's Meinhardt-Reinecke and then Meinhardt by himself. But he essentially tells you how to get this trace of this intersection cohomology in the Grothendieck ring, in some Grothendieck ring. So in our version, you could phrase it the following way. So you have to count points U to the R, V to the D. There's some Q power you have to shift, and you sum over all RD, D over R, equal to a fixed tau, that is a rational number. And then there will be X. And here we have the sum, same sum, and here you have traces of Frobenius from intersection cohomology. We have some formula like this, which basically, so you can invert this, and this uniquely determines these numbers. In fact, in some sense, it uniquely determines the sheaf, IC sheaf. And then our theorem is that the function, or we call it FRD, which is minus it's not the same R. Put a big N here. So we have to. And there's this alpha from the gerb appearing again. I put hom in RD generating series minus the limit of this generating series satisfies the same recursion. So you put this in the at the place of the trace. Same thing. And now we see this statement that does kind of hold. Well, so I stated for just Higgs bundles, but that statement you can prove in much more generality whenever you have the smooth k-linear moduli problems. So this, and so that gives you in general proof that the intersection cohomology in all these cases will be given by this strange formula, but this strange formula, you put the alpha here, it gives you the, will be some integral on the course module. And I stop. Yeah. Yeah, this also some DR. So somehow if you actually write this out, then yeah, knowing all these will tell you all these some linear combinations and product here. Yeah, I don't, yeah. Same defining formula. Homology, yeah. Other than it's given by this integral, I don't know. Then it depends what you want to do. What kind of property you will want to know. But, oh, yeah, no. I don't see how. It's good. Would be interesting, yeah. But, yeah. I don't know. Yeah, these integrals are really hard to compute. Yeah, I guess if you have, so these integrals you can compute typically when you can resolve your singularity in the birational geometric way. So if you, yeah, but it's sort of, yeah.
But they do seems to be things like this, and but you need this to translate your dimension.
Yeah. We don't have direct access to this intersection command. It's very special. Yeah. So, but I think in some sense it also just means that all this intersection cohomology of these quotients by smooth spaces are very special. It's not like intersection cohomology of a random singularity. It's very still, it's lots of structure and so on. Yeah. I think.
Can you repeat what you said about the...
Yeah, so smooth Artin stack, yeah. So, you know, in the, okay, probably if the group is finite, right, then the orbifold cohomology of this quotient is some sort of, so basically, right, or this is just, it's something like the cohomology of the inertial stack. Here, yeah. And this right-hand side, if the G is your gamma is a finite group, then this will count the number of points on that inertia. With there's some shifts, and it's also the weight, it corresponds to the shift, and so on. And if, but so this is not the same as just the equivariant cohomology, right? And so in the case when now we put any group, then I don't know what to put here. It's not just equivariant, well, it's not equivariant cohomology, it's something different, but this is somehow, whatever it is, this is the trace of Frobenius on that. It's given by this formula. Yeah. Oh, yeah. So it's very good, very good. If you don't want. So you can look at BGM. So then it depends what the, so then the weight is probably not very interesting, will be constant, basically. So it's better to maybe choose a representation of GM or something. Then like this example where we had A2. So I think for VGM, I think this expression will vanish. But so the way you can typically compute this for GM, so if you have V mod GM, then the only interesting automorphism, is somewhat the origin. GM fixes the origin, and then all the maps from mu r, so from V mu r into VGM, so they are given by, if you take the union of all r, V mu r into VGM, then that is specific torsion, you once said. And this you can think of as living inside 1, e to the 2 pi I. That's some of the best, it's the best explanation for the right hand side. So it happens, they live on S1. And now on this S1, okay, basically the only information is this weight. So what you get is some sort of weight function on S1. And what you should do is you integrate. So this formula you can also see as integrating over S1 Q to minus this weight function against the locally constant function, so against the Euler characteristic. So I don't know what kind of homology that would be, but this, yeah, for every representation you can hook up this quantity. But these are somehow so these, for if you have any group, then this will be the real points, so sort of the compact real group associated with that group and some integral.
Any other? Yeah, so that's you're good.
Okay.